Well, not all chemical reactions have just gases for reactants and products. A lot of reactions are going to have solids or liquids as the reactants or products. So then what do we do? Well, when a solid or a liquid reacts, does the concentration of the part that's left change? No. So, you can think about the molarity of water. How many moles of water are in a liter of water? It's about 55. Well, does that change if I have a teaspoon of water or a bathtub full of water? No, the concentration is still the same. Same with a solid. The molarity would be related to its density. Its density doesn't change. So here we have this, lump of carbon, and here we have a bigger lump of carbon. Well, the concentration of that solid carbon hasn't changed. You okay with that? So because that doesn't change, we don't include it in the equilibrium expression. Could we calculate the molarity of carbon, solid carbon? Yeah, we could. But since it's not going to change, what is the point, right? It would just cancel out. So when we're doing anything with liquids or solids, their concentrations are not going to appear in the equilibrium expression. Everybody okay with that? So in this example, we've got carbon dioxide and carbon monoxide at equilibrium. And their concentrations are going to be the same at equilibrium here, whether there's a little bit of carbon or a big chunk of carbon. It does not affect the equilibrium, doesn't affect the concentrations of anything else. Okay? So we can just ignore those guys. Okay, so this is where writing equilibrium expressions is going to get a little bit trickier. And we need to start paying attention to those phase symbols. Write the equilibrium expression for the reaction between carbon dioxide and water. Unless they say Kp, we're just going to do Kc, especially since we've got some aqueous things here and partial pressures don't work for that. So the equilibrium constant in terms of concentration, we're going to take the molarity of the products, right? So here we have aqueous hydrogen ion. Well, could we have a molarity of that? Absolutely. And that will be raised to the first power, because that's the coefficient here. And then we have the concentration of hydrogen carbonate ion. This is aqueous. It's a solution. Again, that's going to have a concentration. We're going to divide by the concentration of CO2. And all the coefficients here are 1, so all the exponents are going to be 1. Now, this is a gas. We don't typically think of gases in terms of moles per liter, but it is directly proportional to the partial pressure. Okay? So we can definitely calculate the molarity of CO2 in the gas state. We can't put partial pressure here because if we're using concentrations, they all have to be concentrations. If we're doing pressures, they all have to be pressures. What about this guy? Do I put the concentration of water down here? No, this is a liquid. The concentration can't change, and so we leave it out. Any questions? This is something that does trip students up. Okay, so let's do this one. Write an expression for the equilibrium constant, Kc, for this chemical equation. I'll give you a minute to work on that. Okay, what'd you come up with? Kc equals just a CO2. This is a product, it's a gas. Everything else is a solid, so it doesn't show up. So the equilibrium constant for this expression is equal to the concentration of CO2. Any questions? Let's do this one. Write an expression for the equilibrium constant for this equation. Remember to choose the pen before you start writing. Kc equals, what's going to be in the numerator? Chlorine squared. The concentration of chlorine squared, because it has a coefficient of 2. Why don't we have water up there? It's a liquid. Pure liquid, the concentration doesn't change. And in the denominator, what do we have? HCl to the 4th power times O2. Okay? So this is another instance where we're writing equations and we're using those coefficients from the chemical equation. Okay, so here's one. For which of these reactions does Kp equal Kc? When does Kp equal Kc? When the moles of gas are the same on both sides, right? So if the moles of gas that start out are equal to the moles of gas that end up, then all the RTs cancel out, otherwise they don't. So which one here has the same moles of gas on each side? B. This one can be tricky, right? Because you have to ignore solids and liquids. So here, that's a solid. Don't pay attention to that one. We've got 2 moles of gas. There's another solid and 1. So that's no good. Here, the solid doesn't count. We have 3 moles of gas. Again, a solid that we ignore, and 3 moles of gas, so we're the same on each side. Down here, we've got a solid, and then we've got 2 moles of gas, so it's not going to be the same there either. Any questions? I think writing equilibrium constant expressions from the chemical equation is straightforward, right? Products over reactants raise things to the coefficient as the power. The tricky thing is you have to leave out the liquids and the solids. Okay, got to watch out for that.